Hello YouTube viewers. This is another video in this series on restoring a BMW R75/5 airhead motorcycle. This is a 1971 model, short wheelbase, and I'm currently looking at the charging system on this bike. And I replaced the seal behind the alternator on the crankshaft on this bike. And I did it in my shop with a heater running, and it was just too noisy to really add any commentary, but I'll show you the video on how I removed the alternator and the rotor and the diode board, and I'll just throw in some background music and maybe some of those balloons with written commentary, and then I'll come back and I'm going to test all this out with my multimeter, and I'll go into detail how I do that. Okay, before I start testing these charging parts, I'm going to use a multimeter to check these parts out. Multimeter is pretty essential for troubleshooting any kind of engine, electric system, or pretty much any kind of electrical system, DC, AC, whatever. And what I'll be using today is the ohmmeter, part of a multimeter. These multimeters are cheap. You can get these pretty much anywhere these days, and they're not expensive at all. The ohmmeter settings are basically just, they check continuity or resistance in a circuit. I'm not really an electrical engineer, but I'll show you really quick. Basically, these multimeters have a little battery in there, and they'll basically introduce a small amount of voltage out the positive probe, and if it picks that voltage up in the negative probe, it basically will show no resistance in a circuit. So when you see like the 1 there, and I'm on like 20,000 ohms resistance setting. So if I touch those two, you'll see it cycle to 0. That just means the electrons are coming out of the multimeter, going through the positive probe, directly into the negative probe, and the meter senses that there's no resistance in that circuit. You open it and the electrons can't go from positive to negative, and it shows an open circuit. You can try this out on pretty much anything conductive. This is a metal bolt. This is actually an engine mounting bolt. I have the engine out of my bike currently, so while I'm working on it. So you can see just pretty much anything conductive, the electrons can run from positive to negative and it'll show no resistance. If electrons can't go from positive to negative, from positive to the negative, it'll show open circuit again. So the first thing I'm going to test out here is this rotor. These early R75/5 rotors. Basically all the rotor is basically a coil of wire. You can see, I don't know if you can see that on the camera, but basically it looks like a lot of copper wire just coiled around, wrapped around that rotor many times. I don't know how much is in there, maybe could be 50 yards worth of copper wire. And it's connected to each one of these. There's 2 copper slip rings here. And one end of that copper wire is connected to one slip ring. It goes into the rotor. It's wrapped around, I don't know, hundreds of times. Then it comes out. You can actually see here, one wire comes out of the connection to one slip ring into the rotor, wraps around, and you can see it comes out here connected to the other slip ring. And even though it looks like just copper wire, it's not bare copper wire. This is called magnet wire. Magnet wire is basically it's insulated. I think these days they use some kind of enamel type coating, but it's got I think these old copper wire, magnet wire is coated with some kind of lacquer type substance. So basically the wire is insulated. And so the copper wires aren't connecting to each other. So you want to test continuity through your ohm setting from one slip ring to the other, and you want to get continuity. If there's no continuity between these 2 slip rings, it means there's a break in your wire somewhere where it goes into this rotor, wraps around maybe 50 yards worth, kind of like a fishing reel. And then when it comes back out and connects to the other one, it's just not connected. It's broken somewhere. Maybe it came off the connection here on the slip ring, or maybe the wire is even broken in one of the coils somewhere. But basically, if it's an open circuit, the rotor is no good. Okay, I'm testing continuity from one copper slip ring to the other. It's like cycling back to 0, which tells me there's no open circuit here. But the old lacquer coating on this magnet wire, it gets dry and brittle over the years, and it could be rubbing, it could be shorting to the metal housing. And you don't want that to happen either. So I'm just going to test positive to the copper and negative to the housing. Either way, it doesn't matter. Electrons, they don't care. They'll run one direction. And you can see it's still open circuit, so that tells me that this rotor, the windings are not shorted to the housing anywhere. Okay, this magnet wire with the old brittle lacquer coating, let's say maybe somewhere in these windings that coating is cracked and it's sitting on top of or next to another, the next winding that's cracked, and maybe the electrons are jumping across that magnet wire. Electrons, they're just like us, they'll take the shortest route. So you want to check the actual resistance of the whole coil here. And if it shows less resistance than specified, it either means it's a less resistant coil, which could mean less windings, or there's a short within the coil somewhere. The electrons are jumping over and coming straight back to the other one. And I think these old coils, these early airhead coils, were considered 7 ohm coils. I think in 1974 they changed to a better rotor, which actually had, I think, 3 or 4 ohms resistance. So this technically should have between 6 and 7 ohms resistance. And even this cheap multimeter will show that on the 200 ohm setting, the most sensitive setting. Okay, this is getting difficult. Yeah, this is definitely a 70 to 73 rotor because it's showing almost exactly 7 ohms resistance all the way through the rotor. So this rotor is technically good. It's good, but it's got some problems. I don't know if you can see, but I don't know what this is they used back then. I don't think it would be epoxy. I think it might be something they called Gliptol to kind of, when they manufactured these rotors, they put these days it would be epoxy on top of the coils to just kind of keep them stabilized. This is where you can see some is broken off and it's moving around on the magnet wire. And it's very close to being shorted to the housing, just right there where I can see. And this rotor is spinning when the engine's running. And it's just, even though the rotor tests good, I'm not sure if I can trust it as is. Yeah, some of that stuff just fell out. So it's just not stable. I think what I'm going to do is I'm going to use epoxy and just drip epoxy down in here on this rotor and get the epoxy to just kind of coat the magnet wire in this rotor and just kind of stabilize it and maybe give me a few more miles on this old bike. So I'll do that next. Okay, I shook it and all this old epoxy crap, just it's real brittle. It just can't pour it out of this old rotor. This old rotor it tests good, but it's not in good shape. The best thing to do would be to replace it, but a new one of these is $100 aftermarket, and I've already blown the budget on this BMW build, so I'm gonna use this. I'm pretty sure epoxy, I can stabilize this rotor and at least get it to last. Okay, the epoxy I'm going to use, is this 5-minute speed set epoxy with the built-in mixing nozzle. I usually wouldn't use this kind of epoxy because you waste a lot of epoxy. It's nice and then it mixes up for you, but in the end the epoxy freezes in here and you can see you pretty much waste that much epoxy and you don't get much to begin with. You're paying for the convenience of having the little nozzle. You don't want to get any of this on the outside. Because you'll have to clean it off. And this is 5-minute epoxy, so you kind of have to work fast. Oh, got away from the camera there, sorry. Okay, you want to roll. If you do this, you want to keep rolling the rotor until the epoxy gels, and you want to keep it off the exterior. And you definitely want to keep it off the copper slip rings. Okay, the epoxy is dried. I used some fine sandpaper to clean off the copper slip rings there. And this rotor still tests good. I checked everything. Still precisely 7 ohms between the 2 slip rings. There's no short to ground, and there's continuity between the 2 slip rings. So overall, I'm happy. I think the epoxy is stabilized. I didn't show it on the video, but I warmed the epoxy up with a hairdryer before I shot it down in there. The warm epoxy flows better. It gets thinner, but the problem with warming epoxy is it sets up faster. So warming that 5-minute epoxy turned it into more like 3-minute epoxy, but that's just fine with me. I just injected in there and slowly spun the rotor until the epoxy kind of flowed over all that magnet wire and then froze, and it's pretty stable now. It's protected. None of that old epoxy or Gliptol is going to break off and bounce around in there and damage anything. So honestly, I'm satisfied that this rotor won't leave me stranded on the road anywhere. So on to the stator. Okay, the airhead alternator is a 3-phase AC alternator. It basically gets converted to DC by the Diode Board. And there's really not much you can check. These stators don't go bad that often. Just make sure the coils aren't burned up, blackened and charred, and you just want to, the brushes are not worn out and too short. These brushes look like they have plenty of life left on them. They wear out over time and they get shorter and shorter, and you have problems when they get so short they make intermittent contact they basically rub on the rotor here, and that's when you have problems. These are long and they don't look that old, to be honest. And the 3 phases of an alternator basically means there's 3 windings of magnet wire on this stator, and you just want to make sure they're not shorted to ground. Any of the windings you can see open circuit, open circuit, open circuit. So that means none of the 3 phases are shorted to ground. About the only other continuity test you can make is check each phase with each other, and you want to have a consistent reading. These are pretty dirty. It's hard to get a good connection here. I'm getting 0.9 across, 0.8 across those 2 phases. .8 across those 2, 0.8 across those 2, and then they're all 0.8, so that's good. And these brushes are basically soldered onto each one soldered onto a different terminal here. I'm just going to check that. Yeah, they're good. See that one, the bottom one's connected to that. Good. And good. So this alternator is good as well. Now for the diode board. Okay, now to test this diode board. Actually, there's several diodes on this board, and they all work together to create something called a rectifier. This rectifier takes the 3-phase alternating current from the alternator and rectifies that alternating current into a direct current, mostly through these 6 large diodes. There looks like 3 other diodes in here, but these 3 large diodes do most of the rectifying. And when they're rectifying that current, they generate a lot of heat. That's why these diodes are pressed into this aluminum housing, and the aluminum housing acts as a heat sink to help dissipate some of the heat. And the best way to check this board, really just to look at it. First, just look at it and see if, I've heard a problem with these old airheads. Some of these diodes, they're connected to the heat sink on one side and on the circuit board, printed circuit board on the bottom. And I've heard some of these old solder joints can crack and become loose over time, so just kind of try and shake them and see if they wiggle. Make sure they're solid connections, and they're solid connections. And if you look at this board, it's actually actually insulated. Looks like one side of this board is positive and one is negative. This connection goes straight to your battery, and I believe that the smaller connection there, they're riveted onto the aluminum heatsink here, and so that's the positive. That's how you know that's the positive side of the board. And you can check that. You can see where the bolts mount onto the engine, mount this board rectifier onto the engine, have these plastic isolators that basically isolate the positive side of the board, so you know that it won't short out. The negative side of the board, as you can see, it cycles back to 0, so that's actually connected. So the bolts that mount the bolts that mount this to the board are connected to the housing. So the positive side and the negative side. Now the best way to test these diodes would be to use a multimeter on the continuity setting as well. A diode is basically like a one-way door for electrons. Alternating current, basically just like it says, it alternates. It like alternates back and forth. Then it hits a diode, which is like a, forgive my electrical diagram. Basically it hits, that is terrible. Anyway, you can see what it looks like on your meter. You can see I'm using the little diode checker. The symbol is right there. It takes this alternating current. The current hits that one-way door and it becomes direct current. The current only runs in one direction. It doesn't alternate at all. So the current electrons cannot run backwards through a diode. It's a one-way door. So again, your meter on continuity testing, if you're using the 2000 ohm, and your meter will have like a symbol of a diode there for checking diodes. Your meter will send out electrons over from your positive to your negative. And again, if those electrons can make a connection, then it'll show a closed circuit. Electrons can go from positive to negative and you're good. So if you take your continuity tester, your multimeter, and put positive here and negative here on this side of the diode, it will work. The electrons can run through that diode to the negative side. But if you reverse that, the electrons from your positive probe cannot run through that one-way door and make it to the negative, so it'll show an open circuit. So we're going to test this diode board this way. This is the positive side. So in theory, you should not get any current from the positive side of this. I don't know if you can, that's the best view to see that, but from the positive side of this rectifier board to any of these phases, you should get an open circuit. Basically, the diodes are blocking the electrons. Going in that direction. But your alternator is putting out the AC current through these three terminals, so put the positive side of your meter there, and it'll send electrons through these diodes, and you'll see you are getting a circuit. It's still somewhat resistive. It's got 0.46, 0.46, 0.47, whatever. As long as it's consistent across them, all phases, 0.48, 0.47, but the electrons are running from each phase to the positive side of this rectifier. That tells me that these 3 diodes are good. Each diode is connected to each phase. Now for the negative side of the board, should be the same thing. The negative side of these diodes should go to the electron should run from the positive side of the diode to the negative side, which will be the phase there. So that phase is good. 0.4748. That phase is good. And that's a terrible. I think my hand blocked most of that, but get the picture. Electrons can run from the negative side to that phase. That tells you that diode is good right there. It doesn't matter where you put your positive probe because these are all pressed together, but you can try it. That diode is good, and that diode is good. Well, we know it transmits electricity in the right direction. Let's try the other direction. Yeah, the one-way door works here. One-way door works on that diode, and one-way door works on all these diodes. So. You could probably test those other smaller diodes by scraping away this protective coating on the back of this board, but I'd rather not do that. I've tested the 6 large diodes which do most of the work, and I'm satisfied. Everything looks good here. No broken solder joints. I'm good to go with this rectifier. Okay, the last thing I'm going to check here is this cable that basically just connects the 3-phase current from the 3 phases of the alternator to the diode board rectifier. I checked. In theory, this should be really simple. I mean, this is just a copper wires. They should show absolutely very little resistance from one connector to the other, but just like that mounting bolt there. But I was getting some really erratic readings. I tried checking this earlier, and it's just bouncing around. I've got to shake it. Got to shake the probes. And sometimes I was getting good readings, sometimes I wasn't. Usually that just means the connections are really dirty. I took some of the connections out. You can get these connectors out by using a very small flathead screwdriver up in this. Be very careful. These old plastic connectors are very brittle. You don't want to break that. We slide that up in there and gently pull out that connector. Basically, you're depressing a little. I don't know if you can see that on the camera, but you can depress in that little flap there, and it allows you to slide that out. I slid that out on 2 of these just so I can check the condition of these connectors. They're pretty dirty. I tried cleaning the connections out with this electrical contact cleaner. It improved somewhat, but not good enough for me. And you can see these copper connectors aren't in the best shape. There's one that's kind of worn down to the copper. I need to insulate that with something. I've got some liquid electrical tape somewhere. I can just drop on that, or just pretty much anything. If I had any of that epoxy left, I'd drop a little bit of that on there, but that gelled a long time ago. So I'm going to use that liquid electrical tape on that. But first I'm going to clean out these connections thoroughly. You can look down in there and you can see that old copper is kind of greenish. It's just not clean enough. It's not making a really good connection. It's corroded. For a 45-year-old copper wire, you got to expect that. It just needs cleaned. And I'm going to clean this using vinegar and salt. I'm going to make a glass of vinegar, put a little salt in there, and just dip these connections in there and let it sit for a couple of hours, and then dip the other one in, and that will thoroughly clean the copper. And once you get it out of the vinegar salt mixture, you need to thoroughly rinse off and clean the copper, or the copper will basically degrade pretty rapidly. So okay, just plain white vinegar, cheap. Add a little salt. Well, the wife's going to wonder where all her salt went, but I have my priorities. And let the salt dissolve. Actually, add a little more. Yeah. And what did I do with that connector? Oh, there it is. Okay, I'm just going to dip this connector, old dirty connector, in here. And let it sit for 1 hour, maybe 2. I'll check it after an hour. Okay, all finished with these charging system parts. I basically used vinegar and salt to clean this connection between the alternator and the regulator, the diode board. And the vinegar and salt mixture, it's roughly a cup of vinegar to a tablespoon of salt. It just creates an acid that eats away and cleans the copper, and it helps clean the contacts very well. You have to leave it in there maybe 30 minutes to an hour, and then you have to rinse very well with water, and then you basically use baking soda, mixture of baking soda and water to neutralize the acid from the vinegar and the salt. You just mix some water with baking soda, dip this in there for about 10 minutes as well. It neutralizes any acid left over from the vinegar and salt. And then you rinse this very well again. And then you just let it dry out completely. And after this, I'm getting pretty consistent continuity readings with my meter on this cable. And I've also cleaned all the contacts off on everything. I used some really fine sandpaper and cleaned off all the contacts on both the diode board and the alternator, even the brushes as well. So basically I did this because I really don't want to lose any watts whatsoever, any power whatsoever from the alternator to the diode board, and this connects to the battery, directly to the battery. The reason I'm doing that is these early /5s were known to have a really weak charging system. I think the maximum watts this alternator will generate is 180 watts. And it only does so at fairly high RPM, which is a weakness on these /5s. 180 watts is plenty if you're not going to use a lot of accessories. I don't use a heated jacket or anything like that, so 180 watts is fine with me. I don't have lights all over my bike, just the basic lights that came on the bike, so I'm happy. But what is a problem is the high RPM weakness with these alternators. If you're doing highway driving, it won't be an issue, but if you just do around town, stop and go, traffic kind of driving, you'll probably have to charge your battery a lot, because you'll never reach an RPM high enough to really charge your battery with this setup. And since I plan on doing mostly around town driving, it might be an issue I might have, but I'm not that worried about it. I have a good charger. If I have to charge my battery every once in a while, so be it. And if you are worried about it, basically these parts are still good. I'm confident that the rotor is in good shape now. It won't fail on me. The epoxy pretty much potted all the magnet wire in there, and it still tests great, so I'm not worried about the rotor. The alternator appears to be good. The diode board rectifier tested out good, according to my meter. The final test I won't be able to do until I get the engine running and test the actual wattage output of this system, but I'll make another video and check all that when I'm done with the bike. And best of all, checking this system and getting it ready to go cost me all of $8. I think the epoxy cost me about $8. Everything else I already had: the vinegar, the salt, the baking soda. So I'm good to go. I'm not going to video putting these parts back on the bike. A video taking them off. It's basically the same process. Just stick that back on. Alternator goes over that. 3 bolts and the 4 bolts for the diode board. Should be easy. Just follow the torque recommendations for the 3 bolts for the alternator and the single bolt for the rotor and the diode board, and should be good to go. Hope this video was educational and helped somebody out there, and good luck to all, and goodbye for now.